Okay, guys, recording in progress. Welcome to our extra class today, July 12th, 2022. In the morning, we talk about dimensionality reduction and the principal component analysis. And we started with the clustering, with k-means, how k-means algorithm work in unsupervised learning models. Then we took the expectation maximization and the mostly likelihood. Then we how to optimize clustering. Then we talk about mixture model and Gaussian model, probabilistic models, Bayesian models in unsupervised learning. Then we continue on principal component analysis as feature extraction technique and dimensionality reduction technique. And now we will start on anomaly detection, and we will cover the following topic. This is those handouts I will share right now will explain the thing that I uploaded them to OWL, like the first one, which is the cross-validation and learning curves things. You can read those handout, and if you want to watch the videos, you can watch them in YouTube channel on the series that we have. So, and it will give you like an introduction to neural networks. Then also there is anomaly detection problem that explained by Andrew NG and Gaussian distribution. I applied most of those in my paper, so my paper would explain most of these things that we used. And now we will start with my two papers that I use with anomaly detection during my PhD journey. And it's already uploaded as anomaly detection extra. Can you see my full screen or my black screen, guys? Full screen. Okay, sounds good. Thank you. So the outline, the first three, it's not part of the course. The network security part, which is Bayesian optimization with machine learning algorithm towards anomaly detection. Then in the second problem, which is multi-stage optimized machine learning framework for network intrusion detection. So what we did in the first paper. This is the introduction that the computer network and internet have become an essential component of any organization in this high-tech world. So this is what is the problem motivation. There are traditional protection mechanisms that include firewalls, user authentication, and antivirus program integration. But we have what we call it intrusion detection systems. So to that end, what we did, we investigate the performance of the optimized machine learning algorithm using Bayesian optimization to detect anomalies. How we did that also, what is another contribution? We enhanced the performance of a classification model through the identification of the optimal parameter toward objective function minimization. Then we use a state-of-the-art intrusion detection data set, which is UNBISC 2012, which is designed, sorry guys, which is designed and published by the University of New Brunswick Security Center for experimentation and validation process. To the best of our knowledge, it was no previous work have adapted or adopted Bayesian optimization using this data set. So here we are showing like a framework of our model. We took that data set, we split it into two parts, into testing and the training data set. Then we select a random sample. Then we did the normalization, and we talk about normalization or feature scaling before. Then we use the support vector machine, the random forest, and k-nearest neighbor algorithm. Then we put Bayesian optimization. We got the final model. Then we test it on our testing data set to classify the attack and normal network traffic. So the data set, this is the description of data set. So in your project, I need a description of each data set. So this is how we do research. I'm trying to train you how to do a research paper. So Information Security Center of Excellence, ISCX 2012 dataset was used. Dataset consists of 1.5 million network traffic packet collected over 7 days period with 20 features being defined. So the dataset 1.5 million, 20 feature, and its target network traffic. The training data contains 30. The training data, the random sample that we select, contains 30,000, almost 31,000 of normal traces and 15,000 of attack traces. The testing data consists of 13,000 normal traces and 6,000 or 6.5 K of attack traces. This is how we do this. And how we do the normalization, we do the min-max normalization. And we talk about this earlier in this course. So, hyperparameter tuning. We use the optimization as we talk in the optimization sessions before, that we use it for hyperparameter tuning. What do we mean by hyperparameter? We optimize the algorithm parameter to get the best performance of the machine learning model. So, the Bayesian optimization method tries to minimize P, which is minimize G of P, where P is the set of parameters to be tuned and G of P is the classifier cost function. Whatever we are using SVM, so J of P, it is to minimize or to tune the parameter of the cost function of SVM. Whatever we are using, linear kernel or Gaussian kernel or whatever kernel that we are using. And for KNN, we are trying to optimize the number of, and we will see now, and with other techniques, what we are trying to optimize, which parameters we are trying to optimize. So here, optimize SVM contour. If you remember the lesson when Andrew and G start talking about decision boundary, these are my data points in the data set. I'm trying to visualize it into 2D figure. And here are the decision boundaries. And here are the optimizer trying to find the best value to get the global minimum, to minimize the cost function till convergence. So here, objective function model, this is our objective function. Here we are showing it using the contours, which is the decision boundaries. So here what we did, we, for Bayesian optimization for SVM, we use the box constraint C and kernel scale gamma, and we explain this in deep details when we talk about support vector machine series last week. So how many number of iterations that we do for evaluation or optimization? We use 30. Total elapsed time in seconds. These are the time or in seconds that we use to optimize the model using the training data set. When we use the k nearest neighbor, what we optimize only the number of neighbors and the distance, and we use the Mahalanobis method. We have different method with K and N. You can look at it. So we do also 30 iteration, but it took less time, which is 200 or 2200 seconds. Then when we optimize the random forest, which is kind of decision tree for supervised learning classifiers, so we use the method of AdaBoost because, you know, random forest, we call it ensemble decision tree. What do we mean by ensemble? Which use different decision tree techniques to get the result. And we use what we optimize the method, and the best was AdaBoost, and the number of split in the trees. How many split we do in the trees? We use 1004, and it took the minimal time with 771 seconds to build the model on the training data set. So if we see here, if we use SDM with random or RBF, which is the Gaussian kernel, we get accuracy 99.58 with a precision, recall, and false alarm rate. These are the measurement metrics. We'll talk about it next week. So we get a good result with KNN. Also, we get almost the same as SVM, but shorter in time. With random forest, we get a higher one, and with the minimal time, which means the least computation complexity, which is an important. I don't want my model to be heavy or what we call it computationally expensive. So then we run the Bayesian optimization on SVM, then it's improved to 99.95 with KNN to 99.98 and with random forest to 99.98, but we will pick the random forest because it's the minimal on time. Do you see how we connect most of the topic that we talk about from the beginning of the term till today? So you have to assemble these different ideas, these different topics that we talk about to have a good machine learning model. And this work has been published in IEEE GlobeCom Conference 2018, which is one of the top leading conferences in telecommunications. Now, we expand this work to give it more generalization, more deep in optimization. And if you remember in this work, we pick random number of training data. Here, no, we try even what is the suitable size or the suitable number of training data to get the best result. We try to minimize the number of training sample to be used to build the model. Why is this? Because it will reduce the amount of time and reduce the computational complexity. Also in the new work, which is the multi-stage optimized machine learning framework for network intrusion, also we optimize the number of features. And here we try to study the nature of our data set, not to pick the technique like randomly, try and error. No, based on the data and the nature of data, we decide which technique could perform well on the given data. This is what I was talking. Don't use black and white. No, go in deep and pick the suitable technique for your data to be used to build your machine learning model. So the detection accuracy, this is one I wanted to talk about it, that the detection accuracy, most of machine learning papers and research, they just concentrate on accuracy. Sometimes accuracy is not the right measurement matrix that we can use. Because, for example, I'll give you an example. If I have a data set of 1,000 record, 999 record of normal traffic or network traffic, and only one anomaly. So if my model classify the normal traffic, the 999 correctly, and also it's classify the anomaly or the attack, the only one attack record, as normal, which is wrong, how much the accuracy will come? It will come to 99.9% accuracy. But what is our target of the model? To detect anomalies, to detect attack, to detect the abnormal behavior or abnormal traces or record. But it's classified wrong. However, the accuracy measure give me 99.9% accuracy. Is that a good measure? Of course not. So we will use the precision, we'll use the F1 score, we will use the false alarm rate. Those would give me a high value of false alarm rate, which will give me that my model is not performing well. Because sometimes we are looking for the accuracy of the target class. I'm trying to identify attacks, then I'm looking for how many attacks they are attacks and classified correctly. Then I'll divide them on the sum of how many attacks they are classified correctly and how many attacks they are classified wrong. At that time, I'll get a high false alarm rate, which indicate that my machine learning model is not a good model. Then I have to do some other work to get accurate results. Is that clear? When we said the accuracy is not enough. So the detection accuracy is not the only desirable metric for modern IDS. I explain why. IDS need to be computationally efficient to enable the real-time or near real-time detection of intrusions. So if my model is heavy computationally and it took long time to be built, then if I'm using it in online or real time, when I'm using the internet, so this will cause like slow result on the service, which will make the user feel bored or will not use my website or will not use my network or my services. That's why we are concentrating to reduce the amount or the computational complexity in order to make our model not computationally expensive, which means require long time and exhaust our computational resources. Clear, guys? So what to do? There is a need for mechanism that reduce the complexity for IDS without sacrificing its detection accuracy and performance. At the same time, I need to reduce the size of data. I need to reduce it computationally. I need to reduce the amount of memory required, the time to build the model, the execution time in total. At the same time, to have a high performance model, which means it can detect accurately with the minimal required computational resources and computational time, overall computational complexity, with high performance at the same time. How to achieve this? Then this led me to build and it was a novel model, the first, to best to my knowledge, the first model who considered this step to build machine learning model. And it was published in IEEE Transaction and Network and Service Management. And it was considered also as one of the top paper on 2021. And recently we received like an invitation to have a summary of this paper in one of the recent that will coming next month by IEEE as one of the top novel models that been published in the recent 3 years. And I did this work under the supervision of Professor Shami and collaboration of my colleagues in the research group, but it was part of my PhD thesis. So, to that end, what we did studies the impact of oversampling technique. I will talk about this topic right now on the model's training sample size and determines the minimum suitable training size for effective IDS. How I did this? Using the oversampling technique. I'll talk about it right now. Then also what I did, using the learning curve to get the minimum number of the required training sample. I don't choose it like, oh, let's use 500,000 training sample. No, I use the training curve or the learning curve using the cross-validation curve to determine what is the suitable number of training sample to be used in this problem. Before, I used 1 million then it's reduced to 200,000 record need to build the model. So it was almost reduction by 74% of the required training sample size. Like, think about how much time and memory I saved. And I get a high accuracy result. So this is what I want from you guys to do, to be innovative when you're building your machine learning model. For the algorithm, KNN, SVM, you can watch any video, you can read any book, and then you can remember whatever it is. But how to connect these different ideas in machine learning to have an effective model, accurate model, not a biased model. What do I mean by this? I need my model to predict accurately, classify accurately, not guess. Did you get my point? Then, based on this model, we compare between two different feature selection techniques and explore their effect on the model detection performance and time complexity. Then I reduce the feature set size. When I talk about the sample size, I reduce the number of rows, number of records required to classify. At the same time, after I reduce the number of features using dimensionality reduction or feature selection. So I reduce the complexity by the number of training samples, and also I reduce the number of features at the same time, maintaining high performance system. Then the third step, I investigate the impact of different machine learning hyperparameter optimization technique on the performance enhancement of the ideas. Do you see why we call it multi-stage? At the beginning, we do feature scaling. Then we do oversampling, and we will see now what do we mean by oversampling. Then I reduce the number of training sample that required to train the model and get high performance. Then I reduce the number of features, only the important feature I use to build my model. So I reduce the complexity from two sides, from feature set size and from the sample size or the number of record size. Then I optimize the hyperparameter of the algorithm to minimize the cost function, maintaining the best performance that we can achieve. Clear? Questions still here? Questions? Okay, let's continue. So what do we mean by oversampling technique? Oversampling technique is used to address a class imbalance problem. Let's have this question. When I have a network traffic data set, what do you think, that the attack record is more than normal or the normal is more than attack? Of course, the normal is more than attack. So when I get the data set, normally I'll find a high number of normal records. However, at the same time, I will have a low number of attack records, which is the normal case in daily life or in real-time scenario. But this will cause a class imbalance, that one of the classes in the system has more evidences or more records more than the other one. So I would assume that the machine learning model would identify accurately the normal more than the attack. No solution? No, there is a solution. So we use what we call it synthetic oversampling technique. So we create more record of the attack in order to have the data balance. Almost the number of record of attack are equal to the normal traffic. This would cause a class balancing, which means that I have more samples of attack for the model to be trained. How the technique is doing, you can read about oversampling technique, which is not part of our course, but it's an important thing to know about it. So then different hyperparameter optimization, then different feature selection technique. After that, we use the information gain algorithm. We use the information gain algorithm and correlation based feature selection technique. Then we use different hyperparameter optimization technique, which is the random search, particle swarm optimization, genetic algorithm, and Bayesian optimization. And in the previous paper, we talk about Bayesian optimization in general. In this paper, we differentiate. We have two types of Bayesian optimization, the Gaussian process and the tree-Pargin estimator. We use both techniques. Then we use different machine learning classification technique where optimized and used to detect network anomalies, which is k-nearest neighbor, random forest. And we use the z-score normalization. You have been taught onto min-max optimization. There is a normalization. There are another type of normalization called z-score, which is not part of our course. But if you want to read about it, you can read about it. Or you can go and read my paper. I give like few lines of definition about the z-score on the paper. Data pre-processing, z-score, then we use a smooth, which is the oversampling technique. So we make balance between attack and normal traffic. Then we use the feature selection. We reduce the number of features, which is the information gain and correlation based. Then we use hyperparameter optimization. We use random search, and we call them meta-heuristic optimization algorithm, which is the particle swarm optimization and the genetic algorithm. Then we use the Bayesian optimization, which is Gaussian and tree-Pargin estimator. Then we got the optimized machine learning, and we classify it to normal and attack traces. The first thing, in order to see which technique we could use, the first thing that we have to do is to visualize our data set. What I did, I extract only two features from the set of features for first principal component and second principal component, and I plot it against the class, attack and normal. And you see there is nonlinearity. I have multiple outliers for the first data set, and for the second data set, which is UNSW and B 2015, also I plot it against. And if you can see, there is an overlap. There are some red cells behind this. We can see them here. It's like a two layers. So we prove the nonlinearity of the data. Why? Because if I need to use SVM, I will not use the linear kernel, because the data are nonlinear. Are the data normally distributed? Of course not. If I plot the PDF function, the data are not normally distributed. Based on this, I will not use the naive Bayes algorithm. Do you see how I can pick my algorithm based on the data visualization? So my advice to you, that anyone wanna go with a project or machine learning project, plot your data, use PCA to just extract from the whole set of features, two features, and plot them against the class. Then you can visualize and have a sense how your data look like. So two data sets from the same, which is the University of New Brunswick set, which is CIDS 2017, which is an extension of the first one we used in the previous research. Sorry, I'm still have some little cough from the previous infection, but I'm okay. So we have 3.2 million instances. Look, 2.8 million normal instances and 400K attack. Do you see here we have a class imbalance? While I have 2.8 million instances and only 400K of attacks. And it's 82 features. And one class feature, which means in total 82 features, and the last feature, which is Y, which is the label, which is the class. Based on this, that's why I am forced to do the smooth, which is oversampling, in order to have, but where we do the smooth, we do it on the training sample only, not the test. First step, I split the data into test set and training set. Then I do the smooth on the training set. Then the UNSW, the same thing, it's imbalance. I have 2.2 million of normal and only 500K of attacks. And it consists of 48 statistical feature and one class. Now you will ask me why you use two data sets. In order to prove that my model could be generalized to any network traffic data. Okay. Here we use the learning curve. What do we mean by learning curve? This is the training score for the training set, and here the cross-validation score. We plot the training score against the cross-validation score. When we see the lines are almost near, that means this is the suitable number of training sample that I need. This is for learning curve as simple. You want to study more, you can back to the handout and watch Andrew and G videos about learning curve. But when I plot the learning curve, then when they are become near each other, then this is the right sample to train. If you see here at the beginning, this is without any pre-processing. I plot the data, the training data without any pre-processing, without normalization, without smooth, without anything. Then it showed me that I need almost 2.3 million record as a training sample, which means that the model, if I run optimization and the classification, it will require almost 22 hours if I have a good server to build my model, which is computationally very expensive. This is for the first data set. You see, this is before smooth. Also for the other data set, they are almost come near here, which means like I need 1.25 million record to train the second data set as a training sample. After smooth, see how smooth did. See what smooth did. When I did the oversampling and I remove or solve the class imbalance problem, then the amount reduced with this data set from 2.3 million to almost 600 or 700,000 training sample required. You see how much it dropped? It's almost 1/3 here. 66% of the previous required training sample, I get rid of them when I apply smooth only. Then with the second data set, we reduce it from almost 2.5 or 3 million till 900,000. So almost here also I have like a 40% drop on the number of required training sample. Let's see next what we did. Here we apply the information gain, and here are the information gain algorithm. It depends on what we call it a mutation information score for each feature, which will show the importance of the feature that would be effective to build the model. You see here, there are a set of features that they don't contribute to any machine learning model. But if I use them, I add more memory, I add more feature, more computation for my model with no effect, or sometimes it will be a negative impact. So this is why we are using the feature selection techniques. So we will choose the top best features to classify the model. So I reduce the number of features. With the smooth, I reduce the number of training sample required. Let's see. So here, learning curve for CICDS database after information gain. You see here, we need almost, if it's here around 300 or 400,000. So we reduce the 700,000 after smooth to 300, which is by 50% more. And for the other one, we reduce it to less than 200,000 sample required. When we use correlation-based feature selection, here we use information gain, and here we use correlation-based feature selection. If we see here, it's not performed that much. Here it used the same. So we find that information gain are performing better than correlation-based feature selection. So after we running the random or the KNN and the decision tree with optimization here for the KNN and here for the random forest with CICDS 2017 and UNSW, here are the results that we gained. And here for the random forest. But we find that the Bayesian optimization with Parzen estimator that achieve the highest accuracy with the lowest false alarm rate, with the best precision and best recall. And here we almost reached 100%. So this is performance result, the multi-stage optimized based on IDS framework. And here also with, this is with information gain, and this is with correlation based. So we apply both with feature selection, and we see also here we get a good results. Almost the same with CICDS and almost the same with this one. But here, which one to choose? The lowest computationally. At that time when I defend my thesis, it was submitted and we receive a major revision. Then it was accepted after my PhD. So what is the key contribution of these problems? A proposed novel single stage and multi-stage optimized machine learning based IDS framework that enhance detection accuracy and reduce computational complexity, studied the impact of oversampling technique and determined the minimum suitable training sample size using learning curve, explore the impact of different feature selection technique on the detection performance and time complexity, proposed and investigated impact of different machine learning hyperparameter optimization technique, and it has been evaluated in 3 different data sets, and this showed that we can generalize our novel model. As a conclusion and the future work, you can read them in the paper. I will upload a 2 copy of the first paper and second paper to OWL tonight when I upload the videos to the YouTube. So question on how to use machine learning. Let me show you some code. Let me run the Jupyter. For example, what we did here, here is the learning curve, how we plot it. So we define data frames to do this. Let's see if it's work. Here we divide the data into X-train and X-test. Here we run the random forest classifier. Here we get the training mean, the standard deviation of the cross validation. Then we try to plot the things. Here is the correlation. This is with information gain. Here when we start optimizing, hyperparameter estimation, and those are the result and performance matrix that we get. And here is the confusion matrix. We'll talk about it next week. Here when we use the KNN, and here is the number of neighbors, how we optimize the number of neighbors till we reach 200%, and these are the results. And here is the confusion matrix. Here we use the genetic algorithm optimizer, and those are the gained result. Here we use the PSO with optimization, but I need learning curve. This one. Yes. Here how we build the learning curve, how we plot it. These are the codes, how to build these models. I have, I think, more than learning curve. Just give me a second. No, this one. Here is the correlation. This is the heat map and which feature are correlated and how we can eliminate them. And here are the arrays. And here we plot the learning curve, which reduce the number of samples. And here we are eliminating these are the top best features. Then we have the new training set. Here how we did the grid search optimization. You can see, then we apply the function. Here with KNN, how we did this one was which algorithm? Yeah, here we are choosing the best. Here random forest. Here the heat map. Here the KNN with random forest. Here are the number, the weights, the number of neighbor, what is the distance, how the distance we are using with K and N, and here with the heat map and the results. Here is the F1 score, here the accuracy score, here the micro F1, and here is the rock curve. So these are the measurement metrics we use. So questions till here? Questions? Okay, no questions. I'll stop share my screen. So guys, I received some question from your colleagues about the presentation. So next week, we will have only one class. I'll talk about the performance matrix, then a revision for the final exam, and tell you how the final exam will looks like. This is the first point. Good? Okay. Then we will talk about now the second point about the project presentation. As I told you, the project presentation would be in person with no exception. You will do it in our regular, is Afshan here, the TA?
Yeah, I'm here.
Hi, Afshan, how are you?
I'm fine, thanks.
Yeah, Afshan would be in person in the classroom, in our designated classroom. I will send an announcement. And Afshan will prepare like his laptop for me to join via Zoom to attend the presentation. Sure. Each group member would present, as I mentioned before in the guide and in all the document I upload, that each group member should be responsible for any question within the group. You will do your presentation based on the timing that we given in the guide, how many minutes and how many minutes for questions. All group, please be there at 8:30, and we hope to finalize the things. It will be July 26th from 8:30 to 11:30 till we finish all the groups for a presentation. And then August 2nd, we don't have a class. And August 9 will be the final exam in the same classroom. Sounds good? Questions still here? Okay, no questions. Let me share my screen. We are almost done. Just I want to show you something. Can you see my owl screen? Okay. Okay, about the final exam format, I'll talk about it in a bit. One of your colleagues asking. Okay, so you see here in the resources that my work handout, we call it Anomaly Detection Extra. Then Anomaly Detection, this is Andro NG, Clustering NG, and the videos. These are most of the resources you need. The YouTube series that you can find on YouTube, but if you are like, this is the, if you check here, for example, which one for Andro NG? Yes, this one. If you press here, for example, you will find 112 series, and it will explain the most of the topic. Some of the topic, they are beyond our course limits, but these would be a good reference for you if you need any clarification. Don't hesitate to ask any question. Send me an email. We can have a quick meeting. The final exam format, mostly it will be like a multiple choice and a true false question. I'm not sure if I will have one or two simple questions that you have to write, or it will be all, it's two-part multiple choice and the true false only. I'm still thinking about this. Don't worry about the final exam. I'm not a kind of person who makes things complicated to his student. Don't worry. You will be fine, guys, if you study well. But if you don't study, it's your call. But if you did your part, I'm sure you will do, and you will perform well in the exam. I'm not a kind of harsh professor on his student. I'm always at your side. This is my kind of personality as a university instructor. So I hope this is clear and make you less comfort. Yeah, okay. Okay, Jen, I can classify them. No worries. Is there any question, or shall we stop recording? Okay, clear. Thank you. So if you don't have any question, you can leave. See you next Tuesday. And if you have any question, don't hesitate to ask. I will stop recording right here. Thank you. Thank you, everybody. Thank you.